Hello everybody and welcome to Chapter 5. We're moving into probability distributions. The first one we'll see in Chapter 5 is the discrete distributions, and then we'll move into Chapter 6 and look at the continuous distributions. Now we're only covering a part of Chapter 5. There are a lot of probability distributions that are discrete. We're going to cover the basics all the way from the uniform probability distribution that's discrete and some that aren't. But we're going to also skip over those you might see. You might have heard of before, like the binomial distribution. That's probably the most common discrete distribution that's away from just the uniform. We're sticking to learning how we handle probability distributions so we can move on in statistics and tackle larger problems when we get to our confidence intervals and our hypothesis testing. So Chapter 5, we're going to talk about the difference quickly between discrete and continuous. We're going to talk about how we distribute these things with something called a random variable. And then we're going to look at some measures that go with a random variable. Means, expected value, variance, standard deviation. And we'll finish up by taking a look at risk, just general risk assumptions for risk neutral, risk averse, and risk loving people to see how we can create an expected value play versus a known outcome and see how each group would tackle that problem. So first, just to get a sense of what we're trying to do, say you're a manager of a local Starbucks, or you know a manager. Economy's weak, high gas, high food prices. Starbucks in 2008 said they're going to close 500 stores. So this store that you're concerned with is going to remain open, but the manager's concerned that there's nearby closings might affect her business. Not just Starbucks, but all kinds of businesses shutting down might stop the foot traffic. So she's just trying to figure out, how do we staff? What is it going to look like so we don't affect goodwill by being understaffed, but we also don't overstaff to put ourselves in jeopardy of having our store closed? So historically, a typical Starbucks customer visits their chain between 15 and 18 times a month. So about half the month, a person shows up and grabs something. So based on this, she believes that the average customers will average 18 visits to her store over a 30-day period. So she's going to play to the high end of that range. Now, she has to make some staffing decisions. Too many employees, costly as I said, not enough. It's a long customer line, goodwill might be affected. If she's able to get a hold of a probability distribution, she might be better able to, on an expected value basis as we see, calculate the number of visits someone makes a month or a group makes, or even in a particular hour, group of hours, shift, or day. So all these things can be calculated if we know how our data distributes. Now think back to when we were graphing. When we did a bar chart or column chart or even a histogram, we saw that nice movement of data. If we can map that movement of data to a probability, simply multiply the probability by the amount we saw in frequency, we can create something called an expected value as we see, and will tell us what we expect, or on average, to see in a particular set. So for this, where does it go? First, let's talk about random variables. Now, random variables are pretty easy. You've heard these words before, but a variable is just something, it's a value that we're going to assign something to. And it varies. And when it gets assigned, it's random. Now, the function is on the back end that we're trying to map to. That assigns numerical values to an outcome of a random experiment. So you roll a die. You can get a 1, 2, 3, 4, 5, or 6. Those are the numerical values being assigned to the outcomes. Now, we denote those things by the uppercase letter, usually big X. So you'll hear me say big X from now and again. The random variable, the actual outcome that we see, is denoted by a lowercase letter, usually little x. So you might hear me say x1, x2, x3, and so on. Usually we're mapping the little x to the big X, the outcome, the actual random value that comes out of all this, to the assigned random experiment value. Now there's two kinds of random variables. The one we're looking at right now is discrete. It's countable or countably infinite, but you can count it. Now a continuous random variable, if you think about calculus, what we're thinking about is over a range, there's an infinite number of possible outcomes. You cannot have a probability assigned to something that's infinite because you'd never be able to cap it. On a discrete sense, because you can count the variable, you can then assign a probability to it. So for the discrete, countable or countably infinite can have a value, a probability value assigned to it. Continuous variables cannot, not ever have a particular value have assigned a probability. There are no at value probabilities for continuous. Remember that. So from the discrete sense, think of an experiment where you have this assembly line running. And at some point throughout the day, someone will grab 2 shirts off the line. And if we think about all the possible outcomes that you could get from those two, you could get both defective, first defective, second not, first not, second is, both of them not. So the set that we look at is 0 defective, there are 2 that could have 1 defective, or there could be 2 defective and that happens at one time. You can see how that's countable. So if you really just think about it, there's a 1 in 4 chance they're both defective. There's a 1 in 4 chance that neither are defective, and there is a 1/2 chance, you see this and this, 1/4, 1/4, 1/2 chance that you only have 1. This is discrete. How do we look at these things? Well, this function that I talked about, that when we match it with a probability, when we look at that as a probability matched to a particular random variable, we'll look at it as a probability distribution. And that's going to describe the variable completely. So for the discrete variables, we'll say something called a probability mass function, or PMF. That's used to describe discrete random variables. For the continuous, we have something called the probability density function, or PDF. That's the one where we cannot have at value probabilities. You will have to have it probability set over a range. For both of them, you can accumulate values up to very end of the spectrum if possible. But for the probability mass function, you can have particular at value probabilities, which means you could say the probability of x equals this, x equals say 6, has a probability. If it were PDF, if you said the probability of x equals 6, the answer is always 0. You cannot have a value assigned exactly a value have a probability. And we'll see how that plays out with less than or equal to and greater than or equal to, particularly in Chapter 6. It doesn't even mean anything in Chapter 6, but it does mean something here. So the probability mass function is going to map a random variable to the probability. Notice we're seeing the big X and the little x. For the cumulative, we'll accumulate up to and including a value, and the equal sign means something. We could also say x is greater than or equal to a particular value, and the equals means something. We can also say equals. So all three are in play, and the equals mean something. A couple things to take away here, though. All probabilities that we assign have to be between 0 and 1 inclusive. You can't have more than 100%. You can't have a negative probability. I think that makes sense. However, when you're talking about a particular set of data, all the probabilities in that set must sum up to 1. Like we saw before with the defective, not defective. 1/4 were not defective. 1/4 both were defective. 1/2, one of them was defective. 1/4 plus 1/4 plus 1/2 equals 1. This has to extend over all value of x in your set. Now, we can look at these things in many different ways. We can look at them in tables, graphs, or even mathematically or algebraically, as it says. One particular way, and this is the most common way when we look at discrete, is when we look at the roll of a die, as we talked about a little bit before. I roll a die and I have 6 possible outcomes. 1, 2, 3, 4, 5, 6. They have a very uniform probability set here because it's an unloaded die. There's a 1 in 6 chance of getting any one of those. And each random variable outcome, has a 1 in 6 chance. So the PMF for this, the matching of the pairs, that's what we're interested in. That will lead us to the mean or the expected value variance standard deviation. So keep this in mind. The uniform probability, if you saw it mapped out, it would look like a giant block of cheese. The height of all the bars would be exactly the same. However, what if we wanted to look at it from a cumulative standpoint? For example, what's the probability when I rolled a die I would get 3 or less? Well, there is a 1, 1, 6, 1, 6, 1, 6, there's a 3/6 chance, 1/2 chance, I will get 3 or less. What's the chance I get 5 or less? 5 out of 6. 4 or less? 4 out of 6. But if I ask you, what's the probability that you can, when you roll a die, you get less than 4? Well, you can't include 4 because it doesn't say equal to, so it would be 3, 2, and 1. There's a 1/2 chance you get less than 4. What's the chance you get more than 4 on a roll of a die? Not including 4, that would be 5 and 6, 1, 6, 1, 6. There'd be a 2/6 chance that you get more than 4. So the equals truly mean something here. Be careful with that, looking forward, looking back, and the complementary rules. If you didn't watch the Chapter 4 Short 4 video, go ahead. It explains a little bit about complementary rules. 1 minus whatever you've seen gives you the complement. If we were actually see it written out as a PDF mapping, the probability that x assigns a value, there's a 1/6 chance for all these outcomes. If it's something other than 1, 2, 3, 4, 5, 6, the probability is 0. So mapping to a value of at value 5, since this is discrete, we get a 1/6 chance. If it's 7, it's 0. This is what I said. If you looked at it, it would look like a block of cheese, or it look very uniform. All the heights are the same in the roll of a die. So there's just spun across the x-axis. We roll up to the proper value here for the probability, and you can see that each of the probabilities is the same. Now, I'm going to put this Excel sheet out for you to show you how this is distributed. Each one has been assigned. Let me blow this up a little bit. Each one has been assigned that particular probability. And to make sure that it is a probability distribution, I'm going to sum them all up, and you should get 1. That's imperative. We must do this. Now, the cumulative, all I'm going to do is keep cycling them up until I get to the last one. What's the probability that you roll a die? And this should be greater than or equal to, but this is what we do, is we accumulate. Here for a value, this would be, we want to see, are you less than or equal to particular value? That allows us to see how it's done graphically. Here's another example. What if we look at credit cards at bankrate.com? Now, the first thing we have to do is confirm that this is a valid probability distribution, and we just saw that. Here's what it looks like. So if I look at this data set, here's the number, how many credit cards you carry, and the probability, or the percentage, I should say. All the percentages should sum to 1, or 100%. Bingo, done. So it is a valid probability distribution. Now we can move on. What's the probability that a reader carries no credit cards? Pretty easy, 2.5%. What's the probability that a reader carries fewer than 2? Well, that will be 0 and 1, so we add those two together. What's the probability that a reader carries at least 2 cards? That will be 2 or more, 2, 3, or 4. So if we go back out and look, 0, less than 2, I'm going to sum them up, 2, 3, and 4, I'm going to sum those up, or I could use the complementary rule. If I want more than or equal to 2, I could subtract away less than 2 from 1. That's the complementary rule. 1 minus what I don't want. I don't want these two, and I get 87.7%. I'll leave this here just for a second so you can see it. They're getting the same answers I got. They're doing it again with the complementary rule in place. That's a Chapter 4 idea that we're not covering Chapter 4 in this course, but it does give us a chance to do a quick review. The video should be posted within this particular module. Okay. Moving on, expected values, variances, and standard deviation. Mean, variance, standard deviation. This is imperative for us again as we move forward in statistics. Everything will get a mean and everything will get a standard deviation. That's how we move along. The expected value is the long running, the E of x, E with the x in parentheses, the long running average value over time through many random experiments outcomes. So think about this. I take a die and I roll it, and I get 3. I roll it again, I get a 2, and roll it again, and get a 4. Say I do that 10,000 times. If I add up all the dots that I saw in totality and divide by 10,000, that's the value that I would expect to see on any one roll of die. You'd think the rule of large number would come into play here with that many rolls of the die. That's what the population mean would look like for one roll of a die, mean value. That's also a way it can be done, this mean, by multiplying the probability that you have times the outcome. So 1 times 1, 6, 2 times 1, 6, 3 times 1, 6, 4, all the way through 6. If I sum up all those multiplied pairs, that too will give me the expected value. So if I look at the case of the die, if I multiply each pair 2 by its probability, 3 and so on, and sum them all up, I get 3.5. But I would never be able to roll a die by itself and get 3.5. But that is the mean. That is the average roll. So just because you don't see it doesn't mean the average doesn't exist. This is the play for a game of craps, the die game. Notice if one roll of a die gives you an expected value of 3.5, if I rolled 2, I'd get 7. The most likely thing that you'd see on any pair would be 7. 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, 4, 3. That is the most that you would see, obviously, but is also the basis that you would expect that to be. On a roll of die, you'd expect to see a 7 on any one roll. That's the long-running average value. The variance is just like what we saw before. Once I calculate the expected value or the mean, I'm going to take it away from the outcome that I would see, 1 minus 3.5, 2 minus 3.5, take each and square it and multiply it by its probability, and sum them all up. Sound familiar? This is what you saw initially for the creation of a variance, x minus its mean. You just assumed that all the probabilities were the same. Kind of funny like that. You assume that kind of outcome. Well, this is this in a uniform sense. This probability doesn't always have to be uniform. It could be something a little bit different. Imagine you played a game with loaded die, but in the end it would always sum up to 1, say 1, 6, 1, 6, 1, 6, and then you'd have one that was 1/12, the other was 1/12. I don't know. But you could be able to figure this whole thing out. My numbers aren't going to add up, but this doesn't have to be uniform. So you can calculate that variance and the standard deviation by taking a square root. So let's go back here for a second. Let's take a look at a problem where we say, I would like to know from an owner of a car dealership in Chicago, compensation program based on performance. If you're superior, good, fair, poor, you get particular bonuses. A probability has been assigned to each of those possible outcomes. Now, how you get your performance, I don't know. I'm just here to calculate expected value and bonus, and then the variance. So what I'm going to do, take each and I'm going to multiply. Notice what I'm doing? I'm getting the expected value. So when I sum them all up, a person would expect to get a $4,200 bonus. You can't get a $4,200 bonus, but that's what the expected or the average would be. Then what I'm going to do is multiply the probability, and I'm going to multiply it by taking the bonus minus the mean squared, and I do it for each, and then I'm going to sum them all up. So my variance is this, but my standard deviation is the one that's important. It's $3,150 some dollars. So I'm able to calculate those values. Now I could do something with this. Now I know the mean and I know the standard deviation. Pretty slick. Here's another way to do it, much like I just did, but the results are exactly the same. Again, I'll put this information out in the Excel file for you. The last thing we want to talk about is risk. Basically, just to show how we can use risk and expected value. 3 things we want to look at: risk neutral folks, risk averse folks, and risk seeking folks. Risk-averse folks, they want a reward for taking a risk, and they'll even turn down the prospect of having a positive outcome over something that you'd know exists. They might even decline it just because they don't like the risk. Risk neutral, as long as your expected value is greater than what was told, they'll take it. A risk lover will always take it, no matter what the outcome. So here we go. Suppose you have a choice of receiving $1,000 in cash or a beautiful painting from your grandmother. Someone has told you that it has three possible outcomes. It can be worth $500, $1,000, or $2,000. And here are the signed probabilities for each. What do you do? Well, what I would do, multiply each by its probability, and you find that in the end, the expected value, E of X, equals $1,050. A risk-loving person would take the bet. A risk-neutral person would take the bet. A risk-averse person may or may not take the bet because this value, even though it's more, may not be up to something that they're willing to do. So in that case, the risk-neutral or risk-seeking people would definitely take it. The risk-averse person may or may not. So that's it for Chapter 5. We're going to move into Chapter 6. I know it's not a lot, but in Chapter 6 we're going to move into the continuous. It'll get us into this thing called normal distribution eventually, and t-distribution, and that's really the beginning, the guts of what we'll do in statistics as we move from descriptive statistics through Chapter 7 into inferential statistics. That's the back end of this, where we're going to draw samples and infer things about populations.